Hi everyone, my name is Mohammed and I'm a PhD student in the School of Computing and Engineering at University of Missouri, Kansas City. I will present our paper titled Your Eyes Show What Your Eyes See, a challenge response anti-spoofing method for mobile security using corneal specular reflections. This is a joint work with Khalid Al-Maliki and my advisors, Dr. Baekhyung Choi and Dr. Sejian Song. Facial recognition becomes the most widely adopted touchless biometric authentication because of its contactless and non-invasive process, especially due to the recent global pandemic caused by COVID-19. The quest for touchless biometric authentication methods grows ardent. Today, almost all smartphones and surveillance devices offer facial recognition applications as a multi-factor security for devices access control, financial transaction authentication, and personal data security. Facial recognition vulnerability to presentation attacks. Vulnerability to presentation attacks, also known as spoofing, poses a great challenge to facial recognition usability. Presentation attacks occur at the biometric sensor level. That's why liveness detection against spoofed artifacts like photos, videos, and masks become a challenging task for facial recognition, as it cannot assess the physical presence in unsupervised environment. According to the Fast Identity Online Alliance, there are 3 levels of presentation attack scenarios to be tested: level A, level B, and level C. Level A attacks are quite simple to carry out and require little time, expertise, and equipment. Also, the biometric characteristics are quite easy to obtain, such as printout of face image and a tablet display of face photo from social media. Level B attacks require more time, expertise, and equipment, and the difficulty to acquire the biometric features is higher, like creating 2D paper mask and a video display of face with movement and blinking. As you can see, level A and B are easy to generate and present to the sensor without enough knowledge about the operational details of facial recognition authentication system. However, level C attacks, including 3D silicon and realistic masks and a 3D face model using VR, is very difficult. Several presentation attack detection techniques have been proposed to identify liveness against level C attacks. These techniques can be classified into 3 types. First, hardware-based techniques, such as light field camera and true depth camera. Second, motion and challenge response techniques, such as eye blink detection methods, which track the eye movement to detect the liveness. Third, software-based techniques, such as local binary patterns analysis, to analyze micro pattern in the facial images. The principal limitations of hardware-based techniques are high computational overhead and expensive devices costs. As you can see in the Face ID technology, we have multiple sensors in one device. In addition, challenge response and blink detection techniques are not useful for replaying attacks. Also, the local binary patterns analysis approach cannot work with sophisticated attacks, as the quality of presentation attack artifacts improves and the difficulty in generating those attacks decreases. Achieving reliable liveness detection with the existing method alone remains challenging especially in low-end devices. The main goal of this research project is to validate the idea of your eyes show what your eyes see for face liveness detection. So, when user attempts to authenticate, our method creates multiple image buttons on the authentication screen in different frequencies and sequences as a challenge and captures meaningful corneal reflection responses from users' eyes using front camera. We proposed a software-based face presentation attack detection approach named Your Eyes, which uses screen display as a challenge and corneal specular reflection for authenticating the liveness against presentation spoofing for mobile security. We design and develop various machine learning techniques to identify reflective patterns and perform authentication, including eye image extraction, reflection localization using MobileNet version 2, image sober resolution using SRCNN network architecture, feature extraction using VGG16, principal component analysis for dimensionality reduction, and classification using support vector machine. Your eyes architecture. As you can see in the figure, our method consists of three modules. First, challenge and pattern detection. Second, feature extraction and classification. And finally, data augmentation and training. Challenge and pattern detection module performs challenge generation and face detection using a pre-trained model to identify faces in collected images. After that, we use facial landmarks detection model to return right and left eyes in detected face. Next, we use reflection localization to detect reflection from eye images. And after that, we apply image sober resolution function to recover high resolution corneal image from reflective pattern images and improve their quality. The data augmentation and training module is responsible for creating patterns, augmenting reflective images in different conditions, and generating datasets. Feature extraction and classification module receives high-resolution reflective pattern images from challenge and pattern detection and performs feature extraction using CNN-based feature extraction function to learn new set of deep learning features from reflective pattern images. Then we use principal component analysis to reduce the dimensionality of extracted feature vectors into the optimal dimensional space. After that, we use support vector machine for labeling reflective pattern images at the training and enrollment stages and making predictions for authentication. At the data augmentation and training stage, we created 15 challenge buttons that include 8 black and white images, 4 black and white alphanumeric images, and 3 color buttons. We then built two types of datasets. First, the eye reflection dataset, which consists of 1,300 eye images that contain the reflection of screen challenge. We used this dataset to train the reflection localization model. The second dataset is the corneal reflection dataset, which consists of 1,080 reflection challenge images. By augmenting 72 images from every 15 buttons for support vector machine classification. As you can see, we collect eye images from diverse environments, including daylight, darkness, indoor, outdoor, and wearing glasses. Implementation. We have implemented your eyes in Android, iOS, and web using React Native cross-platform framework. We also utilize TensorFlow, JavaScript package, and Google Machine Learning Kit in our app. We have conducted extensive experiments using our implementation in Android, iOS, and web application for PC to evaluate its performance in the real-world scenarios. Evaluation of reflection detection model. We evaluate the reflection detection model using mean average precision and mean average recall to quantify how the model performs across images in our test datasets. We train MobileNet version 2 to detect reflection in 3 devices. As you can see in the table, our model achieved very high accuracy. Evaluation of authentication. We perform authentication delay experiments using React Native mobile application with TensorFlow package on both Samsung Galaxy S9 and iPhone 11. Overall, the authentication delay is less than 300 milliseconds. The support vector machine classifier accuracy is better than 99%, and the training time is 0.43 seconds. Our application size requires around 180 megabytes memory, and there is no power drain during the normal smartphone operation. Evaluation of presentation attack detection scenarios. In our experiment, we have evaluated our method with 3 levels of presentation attacks: level A, level B, and level C. We focus on the effectiveness of the proposed liveness detection method alone, without combining other face recognition modules, such as Face ID and Face Unlock in Galaxy S9. Level A attacks. To test level A attacks against our method, we prepare both paper printouts and tablet display of face images. We use Samsung Galaxy S9 and iPhone 11 cameras for the level A scenarios. Our method detects all level A attacks as spoof due to the deformation and lack of complete reflection images around the corneal area. Level B attacks. To perform level B attacks, we printed 2 paper masks on heavy cardstock papers. We altered some of the masks by making small eye holes and wearing glasses. The covered eyes in mask 1 are classified as spoof due to the lack of corneal reflection for the challenging button. Even if glasses can reflect some image patterns, it's still classified as spoof because the reflection images are not in the right reflection location. Also, it's very interesting to see the result of the mask too. Even if it has small holes, the reflections are not acceptable because the mask becomes obstacles distorting the reflection. Finally, level C attacks. We evaluate the level C attacks against our method using realistic silicon mask. First with eye holes by wearing glasses, and the second with fake eye images covering the eye holes. The level C attacks are correctly predicted as spoof due to the lack of corneal reflection images around the corneal area. Conclusions. Your eyes is the first software-based human liveness detection method, realizing the idea of your eyes show what your eyes see for mobile device security to the best of our knowledge. We design and built multiple machine learning functions to identify reflective patterns and perform authentication. We have also created a couple of machine learning datasets, such as eye images for reflection localization and corneal reflection images for super resolution and classification for learning liveness authentication. We have built a lightweight machine learning package for Android, iOS, and web applications. Our liveness detection method can be used either as a standalone human liveness detection application or for mobile and IoT device applications as a complementary software solution for touchless biometric systems. We have demonstrated that your eyes provides an accurate and efficient presentation attack detection using only a front-facing camera without using any extra expensive sensors. Thank you so much for watching.